Okay, Keda, thanks for the introduction. As you see here, I want to talk today about some aspects of, on the one hand, generating semantic metadata, and on the other hand, how to query these kind of metadata from a more user-oriented point of view. What's the structure of my talk? I will start with some motivation why these topics are important from our point of view. And then I will have two main technical topics today. One is how to extend the well-known Mediawiki environment with some semantic aspects and what kind of added value you get from adding these kind of semantic aspects. And the second part of my talk will address how to provide natural language interfaces for querying knowledge bases and how to support the adaptation of these query interfaces to different kind of domains, because that is typically one bottleneck you have when you provide these natural language interfaces. And then I will conclude with some outlook on future topics we are investigating. Okay, let's start with the motivation. Well, when you think of the kind of applications a lot of people are interested in, integration is always a very important issue. So you see all these environments popping up to integrate some component applications into more bigger applications. We have these recent developments like Yahoo Pipes on the one hand or Google Mashup Editor on the other hand. But basically, it's some kind of manual task you have to do in order to bring up that kind of application. And what you see in the background are typically rather simply structured data models that are the basis for bringing these kind of applications together. What we currently address is what we call the notion of content integration, where we are interested to bring together content from various resources. And these resources come in various kinds of data models. So you have semi-structured sources. You might also have some textual sources. You might also have multimedia sources. And what is, from our point of view, a very important aspect to really be able to do that integration on a more content-oriented level is that you need some kind of semantic metadata to describe these various kind of sources and therefore have a better basis of how to define the relationship between these different kind of sources. So that is the integration aspect that will be addressed by looking into that semantic metadata area. And then the second aspect is when you think of how to access information sources. Well, we are all familiar with these keyword-based search, and one could say, well, when you talk about what you could tell these, call these short-tail queries in these very popular domains like music and that kind of stuff, that works very well. But when you go to the other domains that you could call these long-tail queries, where you have specific domains, not these very big user communities, there is some advantage of providing a little bit more of semantics to describe these kind of domains and then being able to do some better kind of query answering in these domains. And that will be the second aspect I will address in my talk today. Just to give you an example what kind of application we are currently investigating in one of these EU-funded projects we are involved in Karlsruhe. One partner is the United Nations in Rome, and they have a big department that is addressing fishery and agriculture issues. And for example, they are developing some kind of fishery assessment system in order to be able to answer queries about why you see, for example, in that example, the stock of tuna is depleting, and that are the kind of issues they have to address by getting a lot of queries from all kind of countries that are supporting that United Nations organization in Rome. What you have there as a typical situation is that you have a lot of different kind of resources that are available. You have some documents about fish species. You have databases that describe the current situation in various oceans, for example, and what's going on in different kind of countries that live to some extent on fish industry. Then you have organizational aspects being described. So we have really a very heterogeneous kind of collection of resources. And in order to come up with applications, still one of the major bottlenecks, how to come up with all these semantic descriptions. And therefore, one challenge is how can you provide environments that are usable for a lot of people in order to provide some kind of semantic information without having first to study for 5 years all kinds of logics, doing a PhD in the semantic web area, and then being able to provide that kind of data. So how to provide a path that is accessible for a lot of people in the end. And then the second point is how could you come up with user interfaces based on natural language so that they are rather easy to use in the end. And then you have all these problems of how to handle these ambiguity issues when you pose these natural language queries. And also you have to handle the effort of how to move from one domain to the next one, because if that effort is too high, in the end it will not be feasible to use that kind of natural language technology in the end. Therefore you have to think about how to reduce the effort of making that adaptation step from one domain to the next one. And that is part of that Oracle system that we have developed in Karlsruhe, and I will indicate some of these aspects. Okay, so let's come to the first part of my talk, how to use these rather straightforward wiki environments in order to enhance them in a way that you can really provide semantic metadata in these environments. Okay, here you see my running example that's related to Croatia and Europe. And the example is that you talk about a specific island in Croatia called Brač. And then you see these typical links you are familiar with in Wikipedia. So Brač is related somehow to Croatia. It's somehow related to Adriatic Sea, for example. It's also somehow related to tourism because that island is to some extent living on tourism, but also to some extent on fishing. And what you have here is the typical structure. You have these individual pages and that are linked to each other. As a human reader, you can put in much more semantic relationships when reading that page compared to what a machine is typically able to do. So when we think of these kind of links, well, we have Brač, and then we have all these kind of other entities like Croatia, tourism, fishing. And from reading that page, as a human reader, we are well aware, that we have something like a belongs to relationship between Brač on the one hand and Croatia on the other hand, or that Brač, for example, is located in the Adriatic Sea, or that we have some cities located on that island, or that Brač lives, for example, on tourism. And then the question is, could we bring in some more semantic stuff into the basic Mediawiki system in order to be able to capture these kind of semantics that are very easily catched up by a human reader, but are not really available on the machine level when you interpret these kind of links. And that is the basic idea then of how we approach that kind of scenario. We have, in essence, two types of extensions. One is that we are able to type these links that relate Brač to tourism, for example. And second extension is that we also type these attributes that are around. So when you talk about the number of inhabitants of a city, that you can really be precise what kind of meaning that attribute has in the end. So that is the standard syntax you are using in that Mediawiki environment to define these links here between Brač on the one hand and Croatia on the other hand. And we stick as far as possible to the available syntax in order to make as less modifications as possible in order to come up with our semantic extensions. And here you see the two types of extensions that are added in the end. So we precisely define the type of link between Brač on the one hand and Croatia on the other hand. So we know that there now we have defined a belongs to relationship between Brač and Croatia. But the user is free what kind of name he wants to use for that relationship. So there is no predefined ontology that to some extent preoccupies what you are allowed to do in the end. We are still free here to say belongs to, or you could also say is part of or is associated with. But we keep here the freedom that in order to support that bottom-up definition of semantic relationships, the user is free to choose the name he really prefers. You have a question?
Yeah, so how did you decide to use belongs to in this case? Is it just because it is A?
I did not get your point. What was your question?
Okay, so use the relation belongs to in this case, right?
Yeah.
So this is due to the fact that is A being used? Is A.
No, that is not an that's exactly not an is-a relationship here. You see the text in the conventional Wikipedia environment would be Prague is a Croatian island. And what you have seen on the page before, here you see is that for whatever reason a link was defined between Prague on the one hand and Croatia on the other hand. So, and now we can decide what kind of link do we want to define between Prague and Croatia. And here we decided we call that link belongs to. We could also have chosen other kinds of links, but that is the decision of the user what kind of link he wants to introduce in order to relate these two elements.
The sentence could be a Prague is a Croatian friend, right? So in this case,
There are different kind of textual representation that might end up in the same kind of semantic link, or that might end up in different kind of semantic links. So that's the decision of the user who is typing in that text and making that decision what kind of type. Yeah, the user is inputting that kind of text in the usual way with this slightly modified syntax, but then you are free to say, well, I call that a belongs to link. Okay?
And the fact that Brock is the owning concept is because it's on the Brock page. Because these relations here don't actually say Brock belongs to Croatia.
Well, my examples are you have that specific page describing Prague. Yeah, that defines the context you are in, and then you define the links you think are relevant to describe that entity on a more precise level. Okay, and the second extension is that you are also able to precisely define the kind of attributes that are used to further characterize your entities. So here you have that attribute that describes how much square kilometers are associated with that specific island. When you think of that kind of stuff in an RDF context, then you see that in the end you generate two triples out of these two specifications. So one triple is that belongs to relationship between Prague and Croatia, and the other triple is that area attribute that relates Prague to that specific number of square kilometers in the end. So that is the underlying semantic representation that is used. What we exploit in that context is a rather easy, straightforward one-to-one relationship between elements you find in Semantic Mediawiki on the one hand. That is what you see here on the right-hand side. You have articles, you have attributes, you have links. And on the left-hand side, you see to which modeling element in the OWL ontology language these wiki elements are really mapped. So for example, an article is mapped to an individual. So that would be that correspondence. Or when you think of that typed link, we have referred to that example belongs to. That is then mapped to an object property instance. Or when you think of that attribute value, that is mapped to a data type property. So we have a rather straightforward one-to-one mapping between these elements you find in the wiki environment to the formal representation that is based on some subset of that OWL language. And that is not a surprise because the kind of extensions we have defined had been tailored in a way that we can really have that rather straightforward mapping to the OWL environment. Okay, so what is now the benefit of adding that kind of semantic description? Here you see at the top the straightforward page as you find it in Wikipedia today. And what comes on top now is what we call the fact box at the lower part. So here you see all these specific facts that had been provided by the user. So here, for example, you see that fact that Prague now has that belongs to relationship to Croatia, so that is one of these facts. Then the other could be that Prague lives on tourism and lives on fishing. So now you see here in that box at the lower part of the page, what are all the facts that have been specified by the user for describing what he thinks is interesting to know about Prague in that context. We also have some additional features in the background so that you have all these conversions available from square meters to square miles or that kind of stuff. What might be more important is that you can also do some kind of semantic browsing. So you always see here these icons that you can click on. And that provides you with the ability to browse around in the content of your wiki system based on the kind of relationship you are interested in. So here we would say, well, we now know that Prague lives on tourism. Are there other entities that also live on tourism? So that we know, well, maybe there are other towns or other islands around. And when you would click on that icon, you would see something like that as the next page. So you see again that Prague is one of these elements that live on tourism, but you see also other cities like Rio or Dubai that are specified to live on tourism. So that provides you with a very flexible browsing environment based on these typed links. So that is one immediate benefit you get by typing in these links that you can then browse around in that collection of facts in the end. A second important aspect is that by exploiting these extensions, we are also able to generate some of these summary tables in a consistent and very straightforward way. You are all aware that you find these summary pages that in the end are manually maintained. So what are the cities in California or what are the cities in Germany? So somebody has to input that. And when you change one of these basic facts, you really have to think about how to modify your aggregation table. And that is something one really would like to get rid of because that is a manual task, a lot of effort, and consistency is always an issue. So what we provide in order to get rid of that situation is what we call inline queries. So you can really put in these queries into your text that you enter on your wiki page. So they are embedded into these ask tags, and then you can specify your query by exploiting a very restricted query language. Here you see that you can specify a conjunction of atomic conditions. So here we specify that we are interested in countries that should be located in Africa and have some range of population around. So we have that type of conjunctive query here available. And then you have, in addition, the opportunity to define what kind of descriptive elements you want to have in the answer set. So how do you describe the countries you are interested in, by their population or by their borders? So when you then would activate that kind of query, the system would automatically generate these kind of tables so that you see, well, Central African Republic has around 4 million people there, and that are the other countries that have a border shared with them. And by having that table generated, you are always sure that if one of the underlying facts has been modified, that table will reflect that modification. So you have consistency guaranteed, and you have just to specify one set query and not to maintain the table manually. So that's, again, a very immediate benefit you get from that kind of approach. So from our point of view, that is one way of really taking an environment where a lot of people are familiar with, enhancing it with small semantic ingredients, but having then an immediate payoff by getting these kind of additional benefits more or less for free in the end. And I think it's very important that you really show that people get immediate benefit. So otherwise they are not motivated to first invest 3 months of specifying all that semantic stuff and then have the first added value based on that. But when you specify these links on the first page you are entering, you immediately get the benefit from that. And that is one experience we have made, that is a very good way of really attracting people to really use these kind of features in the end. Of course, there are still a lot of open issues, and some of those topics are current work that we are currently addressing. So one question is, when you leave that freedom in that bottom-up process, that you can choose the naming of the links on an individual basis, the question is there some support available to generate some kind of agreement so that a lot of people would use that belongs to type of link instead of naming it in a different way? And clearly, you can then exploit some techniques that are known from information extraction and ontology learning in the background to handle synonym problems and homonym problems and that kind of stuff. So that is one way of providing additional support for that process. Second aspect is what I've shown here is the situation that you enter a new page and then you use the semantic extensions to provide that semantic information. But there are already a lot of pages around, and nobody would like to do the manual process of enhancing these already available pages with that semantic stuff. So one idea is how could you improve or how could you support a process that at least some of these links are generated in a semi-automatic way. And I will address that aspect in a minute, what kind of approach we have available to generate some of these links based on the available information. Then third aspect is user interface aspect, how you can make the user interface still more comfortable. And one aspect is, for example, auto-completion aspects, or also using some kind of templates that users just fill in order to provide these kind of links. And then an ongoing discussion is what kind of additional expressiveness one might add to what we have already available. So what you have currently seen is that we have these binary links, so we can only relate two entities to each other, but sometimes it would be nice to have also n-array links available in order to cope with other aspects. So that is one issue that is currently investigated. Also, it might be interesting to add some more semantic description to these links so that you could say, well, one relationship is symmetric, is a symmetric relationship, but we are currently investigating that very carefully because the experience is as soon as your semantic model becomes too complex, people are not comfortable anymore to handle it in the end. And therefore, we really think about what kind of additional elements we want to add to what we have currently available. So that is ongoing discussion, what might be a useful idea in that context. Okay, so let's address one of these aspects, how you could improve the generation of these semantic links. And one aspect is how could you exploit some learning approaches in that context in order to generate some of these typed links in the end. What is specific in that situation when you want to learn something from a Wikipedia environment is that you have no redundant information in the end. Because you have one page describing one specific entity, and there you find all relevant information. That's completely different to going to the web where you find these millions of pages relating to the same kind of fact. So you need some approach being able to handle that specific situation. What we have done as a solution is that on the one hand, we rely on a pattern-based approach. You will see in a minute how that works in the end. So that is one design decision we have made. And the second decision is in order to cope with that hardly redundant environment, we do that in an iterative way. So we start with some bootstrapping and then improve the kind of things that system is generating in an iterative way. And in that way, we are able to cope somehow with that kind of challenge in the end. Okay, so what is the basic idea? You see here a standard page from Wikipedia about that nice fish, blue gill, in that context. What we exploit in that context is that we just want to learn new relationships that are related to the entity that is described on the page. So blue gill is the anchor. And then we want to learn what kind of links can we extract from that page that is describing blue gill, for example. And we can specify in our system in what kind of links are we currently interested. So you here see, for example, the example that we are somehow related in the relationship where that fish is really living in. So a relationship between the fish and the area where you find that fish. So that is the kind of specification you give for that learning process, what are the kind of relationships I'm interested in. And then what we exploit in our iterative approach is that we exploit a rather simple notion of context. And you see what we use as a context here is some tokens in front of the link and some tokens that are coming behind the link. So for example, we talk here about Quebec, you have some tokens behind Quebec and some tokens in front of Quebec. So that is the kind of very simple context notion that we are exploiting in that learning process. So how is that now done in the end in that bootstrapping in iterative approach? You start with some very few seed elements. So you see here that one seed element would be Blue Jill and Quebec. And then you go to your Wikipedia pages in order to see what kind of patterns you might find on these Wikipedia pages. So you find these explicit link elements and then the context by some text part in front of it and some text part behind it. So that is that simple notion of context. We are using that. And from these contexts, we generate some generalized patterns. That is done in a way as it is known from inductive logic programming, that you generalize the kind of descriptions in order to come up with some more generic descriptions. Clearly, you need some heuristics in order to guide that generalization process so that the patterns that are generated in the end are not becoming too generic. So we have some restrictions on the number of wildcards that are allowed in these patterns. And also we have some restrictions on the number of examples that are still available to support that kind of generic pattern. So there are a combination of some heuristics to guide that generalization process. Then you use these patterns, and then you go again to your wiki pages, and then you find additional instances that meet these generalized patterns. And then you have done the first iteration of your bootstrapping process, and then you have additional instances, and then you can again go to the next iteration and see what slightly modified contexts are then generated based on these new instances you have found. So that is the kind of cyclic approach we are using there. We are also currently investigating to supplement that cycle based on Wikipedia by going with these generalized patterns also to the web to get some information from the web. Then to filter what you find from the web, because then you get a lot of information. So there is some ranking involved. And by that, you can feed in some additional instances into that iterative process. And the results are rather promising when you combine these two kinds of learning scenarios in the end. So the challenges we are addressing here is that you have really these situation that that you do not have a lot of instances available, and therefore we use that pattern-based approach in that iterative way. Also, one advantage of that approach is that you get rid of a lot of that natural language processing. So we do not have to analyze the complete page about that fish in that example, because we do not analyze all these sentences. We just analyze that part of the sentence that is in front of the link and that comes behind the link. So that reduces the effort that you have to invest into that natural language analysis considerably. So that is also one advantage of using that pattern-based approach. By filtering these patterns and ranking them, we can to some extent guide the precision recall ratio. So when we come up with rather generalized patterns, then of course we will have a rather high recall but low precision. So by putting in some filtering function that ranks these generated patterns, we are able to guide the system to some extent with respect to these notions of precision and recall. What we have also found in experiments is a very good indicator of the quality of your pattern is a very simple measure. You just look at the number of instances you find that support that pattern. That is a good indicator about the quality of that pattern. And what you can also exploit as additional information is that you exploit some background knowledge, so that you exploit, for example, some typing information of the elements that show up in the patterns, and that again improves your result in the end. So that is one way of generating some of these semantic links in a semi-automatic way in order to get rid of some of that manual stuff. Okay, so that was the wiki environment stuff. Let me now move to the second part of my talk, that natural language interface aspect. Well, why is that interesting? We think in a lot of application domains, it might be really nice to have some more flexible way of querying the content of the systems you have available. And one way of doing that is provide some kind of natural language interface for addressing that. Clearly, there are always these well-known issues associated when you come up with these natural language interfaces. One is how to cope with all these ambiguity issues that pop up immediately. Also, the question is, how can you come up with a large coverage of the kind of questions that you are able to understand in the end, so that the users are not too restricted in the kind of way they are allowed to specify the natural language query. Clearly, then you need some robustness because you never know what people are typing in when they use these natural language queries. And also, always the question is, how much effort do you need when you have that infrastructure available to adapt that to a specific application domain? And that is typically also one of the bottlenecks that are around. So why is natural language interfaces maybe to some extent a more easy task compared to text understanding when you compare the kind of challenges? Well, on the one hand, typically these natural language interfaces use rather short sentences. They do not have these very long sentences that you have to analyze when you analyze text in the end. Then we have here our assumption that we do not handle discourse phenomena that are typically very valid when you do text analysis. Clearly, when you think of a very nice interface, that discourse handling would be a nice feature, but that is currently not part of our system and makes life much more easy in that context. So there are some assumptions you might put into that interface development that makes life a little bit more easy compared to natural language processing. So just to show you what are kind of queries we are able to handle in the end. So that is taken from some geographic domain and test system. So you could ask, related to some Europe geography, which river flows through more cities than the Rhine, so that you can compare different rivers that are around. I will not go into the details. You just see that in the background, you have to generate rather complicated logical expressions to really cope with the semantics of these kind of queries in the end. What we have available as a system is that system named Oracle, and that comes with two kind of functionalities. One is the end-user functionality. So you pose your query that is then interpreted as you have just seen it. Then there are these logical representations generated, and then you submit that logical representation of the query to your knowledge base. Also, the domain ontology exploited in order to come up with the answer, and then that answer is shown to the user. So that is the kind of end-user cycle. What you also need is the development cycle, and there you see here the developer of the system, because you have to come up with all these lexicons you need in the background to do all that kind of natural language processing in order to understand the meaning of the query, in order to be able to map that to that formal logical representation in the background. What I will discuss later on, one specific design ingredient of the Oracle system is that we have the lexicon split up in two parts. One is a domain-independent lexicon that you have to just develop once. And then you have these domain-specific extensions that have to be generated for each domain you want to address in the end. And I will come back to that issue later on. Okay, so what is the kind of basic approach we use for building up the meanings of these natural language queries? So here the query is, which river flows through Karlsruhe? You see here that we use a compositional approach. So we analyze syntactic elements, like that verb phrase here, for example, or that extension of that verb phrase relating to some prepositional aspects. So by analyzing these individual syntactic elements and composing them in a bottom-up way, we come up then with the complete semantic representation of that query. So that is that compositional approach. That is one of the well-known approaches in computer linguistics to define the meaning of these sentences, and in our case, the meaning of these queries in the end. Okay, what is the specific aspect we address when we talk about adaptation of the system to specific domains? So what I have already mentioned is that we have that separation between the domain-independent and the domain-specific lexicon. The domain-independent lexicon is tailored to the kind of words you find in your queries that have a constant meaning. So that these are the words that are more or less independent from the specific domain you are currently working in. So you can define that kind of lexicon once and then reuse it in several kind of different domains in the end. What we also exploit here in the background is that you can refer to some foundational categories being defined by ontologies in the background. And what we exploit here, for example, is that foundational ontology Dolce that is developed by Aldo and his group in Rome in order to come up with these basic definitions of terms that are then independent of a specific application domain. What is then to be done is when you move to a specific domain, like in our case into that geographic domain with rivers and cities and countries and borders, you have to come up with that domain-specific part of the lexicon. And that is typically the bottleneck to some extent because you have to develop that for each specific domain. And the question is, how much training and how much know-how do you need in the end to be able to define that lexicon? So do you need a PhD in computer linguistics to do that, and then you have a bottleneck because not a lot of people are around there, or are there other ways of generating that kind of lexicon? And what we have developed here is an approach that people that do not really have that expertise in computer linguistics are still able to do that in the end, so that you have much more people available that are able to support that adaptation step in the end. So how is that done in the end? So in essence, we rely on two basic ingredients to support that development process. On the one hand, we have our ontology that defines the kind of relations we are interested in. So here, for example, we have that flows through relationship that relates river to cities. And that is part of these relation definitions we have specified in our ontology. So that are the predefined links that are relevant for our domain. And then the second question is, how is that reflected on the linguistic level in the kind of lexical elements you have to define for your lexicon? So you find here that notion of predicate argument structures that are well defined for verbs in that context. So you know that verb flow that comes with a subject, and then it comes with a prepositional complement that defines through which object that element is really flowing. And then the question is, in order to generate the lexicon, how do you come up with that mapping between these relations you have defined in your knowledge base and how to relate them to these subcategorization frames that are known from linguistics. And here you see the kind of simple mapping that is then provided. Here you see that relationship flows through between rivers and city. And here you see that subcategorization frame that is now specified by the user to capture the meaning of that flow verb coming with a subject, and then you see here the subject is the river, and then you have that complement, that prepositional complement, and that is in that case defined through object, and that is mapped to city. So you know that that complement is related to cities. By having that rather simple interface available, our experience is that really users that just got some basic knowledge about these linguistic elements are really able to come up with these mappings and therefore generate that lexicon in the background. Clearly, you would assume that in case someone having 5 years of experience and a PhD in that area will come up with better structures for your lexicon. Yes, to some extent, but the good message is that the quality of that lexicon that is generated by relying on these people that have just a very limited training in computer linguistics has still good quality. So it's comparable, not on the same level, but it's a quality that you can really exploit in the end. The second thing we are using in order to come up with broad coverage with our grammar is that we first specify some of these mappings, and then we ask users to pose queries. And for each query that fails because some linguistic construct was not defined in the end, we exploit that iterative approach that then we define specifically tailored to that query that missing element for our lexicon. And in that way, we can iteratively broaden the scope of coverage we are able to do, because experience shows it's very difficult to imagine from the very beginning what would be the kind of syntactic constructs people will use to pose these kind of queries. And by then seeing concrete examples, you get a very good guideline what kind of syntactic elements to further enter into your lexicon. So that is an iterative approach guided by the kind of queries users are posing to your system in the end. And that shows that that is a very good strategy to come up with a good coverage of the type of queries users want to pose to your system in the end. Okay, so what we have learned here is that we can provide a translation of these natural language queries into that logical representation to really pose them then as queries to the knowledge base in the end. That we are able to provide an adaptation mechanisms that is usable by non-experts. They need a little bit of training, but not these many years of training, so that more people are really able to support that adaptation process. And when you then compare in some studies that we have done, what are the results when you have chosen the experts compared to what are the results when you have chosen these non-experts, you have rather comparable results in the end. And by having that iterative approach, we are also able to address that coverage problems in a suitable way. So that is rather promising from our point of view. Okay, let's come to the conclusion. But what we have addressed in both scenarios, both in that wiki scenario and in that natural language scenario, is how to come up with some kind of techniques that more people are able to provide the kind of content you need in the end to come up with your solutions. So that is in the wiki environment, clearly related to all these Web 2.0 technologies, how to bring in communities to specify content in the end. And that is related when you talk about these interfaces, how to come up with all these lexicon descriptions that you need in the end. So from our point of view, that semantic extension of Mediawiki is a really nice way of providing an environment where people are really able to come up with a lot of semantic descriptions. And by exporting these facts I have shown in that fact box that are associated with these Wikipedia pages, you can feed them into all kind of RDF repositories and therefore generate a lot of RDF-based facts in the background. And also you have seen by providing that relation extraction technique, you are able to generate some of these facts in a semi-automatic way. And with respect to these natural language interfaces, clearly we need these semantic models in the background, but we have some ways of making that adaptation process more easy and also usable by non-expert users in the end. So what are topics we are currently investigating in order to improve the kind of solutions we have available currently? Clearly, we are still investigating how to further improve that bridge between the semantic web world on the one hand and these community-based approaches from the Web 2.0 world. And we see rather promising steps by combining, for example, these wiki environments as we have made now available with these ontology engineering environments to come up with a very smooth transition from these very lightweight approaches to these more heavyweight approaches. We also think by adding some semantic descriptions, we could also provide better means of integrating that a huge amount of information that is around in all these social spaces, but that are still disconnected to some extent. And by providing some more semantics, we think there is a lot of opportunity to provide better integration. What we always try to do is to come up with solutions that are to some extent easy to use, so that are people not forced to have several years of logic training, computer linguistic training to really do that kind of stuff, and also to exploit some learning mechanisms in the background to get rid of some of the manual stuff that you are doing currently. And clearly, scalability is always an issue, both from a point of view how to come up with a lot of semantic facts in the end. So how can you really support that large-scale knowledge acquisition? And on the other hand, clearly, when you talk, for example, about natural language interfaces, efficiency and scalability is always an issue because you have to have means that you are really able to come up with efficient solutions in that context. So we have some solutions around, but clearly there is room for improvement in all these different kind of aspects. Okay, thanks for your attention. Clearly, what I have presented is based on work of a lot of people in my group. And if you are interested, just go to the web pages of our groups in Karlsruhe, and there you find all these kind of relevant literature. What also might be interesting for you, go to the homepage of our AIFB Institute, because there you see a completely semantic portal that has in the background all these semantic models around so that you can export artifacts about projects, people, whatever we are doing there. So that is one example of a semantically supported portal, and that you can pick a lot of facts just by going to that portal. Okay, thanks again, and I'm open for some kind of questions. Yes, please.
I noticed in your, when you had a query over for countries, you had a category countries. I'm wondering if that category, when you were querying, okay, you had a category in your query. I'm wondering if that category, I'm wondering if that category is specific to, is special in the system, or if it's just a tag that a user defined, and also if that's enough, or if you needed a hierarchy or a list of labels or something for every element.
You see, when you go into that geographic domain, we have an ontology in the background available that describes some basic concepts of that geographic domain, so that you know some characteristics of countries, what kind of relationships they might have. We have seen that in that adaptation process that we have some predefined links. In my example, that was river to city. So we have the notion of river available, we have the notions of cities available, and we know what kind of characteristics they have available. So there is some semantic model about your domain available in the background in order to support these kind of analysis in the end.
Okay, so each element has like one domain that it applies to, like country has, or a country has a country, and then all those relations are specific to that domain?
Well, when you think of ontology engineering, you typically rely on some reuse of already predefined ontologies. So you might find some module about these geographic concepts that could be reused in a lot of different kind of applications in the end. So you do not have to start from scratch every time you move to a new domain in the end. So that is the typical reuse you have as part of your ontology engineering process.
Thanks.
I found this fascinating because I'm new to this, and for this domain-specific lexicon building the structure, how much is the volume work? It's like, excuse me. So like we have like for geography, like I guess historical figure and every kind of structure. Like, is this kind of like like something you plan to outsource to somewhere to do, or like it's like how much the volume of the work?
You see clearly what I have described here was one example system we have developed addressing that geographic scenario that has not a worldwide coverage. So that is currently more or less related to Germany and some geographic elements that are related there. And then we did a specific case study to see when you take people that get just a very limited amount of training in that linguistic area and compare the results with what my experienced people in my team are delivering in the end. And then we compared the results based on these two kind of lexicons that had been generated. And that was the result that was rather promising, that the quality of the lexicon of these non-expert was really fine, not that good as my PhD students are doing that, but enough quality to really deploy the system. That is the kind of message. But we do not have available a system that would now cover all of Europe or all of US. That would still be an effort to do, okay.
Thank you.
Yes, please.
I had a question. As you're looking at natural language queries and things like that nature, do we think as we provide more semantic information behind content that that people will start building that intuition of different types, more long tail, more deeper queries, that they will build the intuition to build and actually write, and then those queries, for example, like the borders, like, you know, right now I don't even, as a user, I don't even think of even asking that question because I know there's not an answer. But as we add more, do you see that if we add more semantic data that we can ask like a question like how many countries have odd numbers of borders and also have rivers running from the north and south? I mean, like these type of queries may not, you know, we don't think of them, but, you know, like, yeah.
You see what I've said in the beginning, you can distinguish these short tail and long tail queries. So we are currently a little bit biased to that short tail scenarios where a lot of people are using that. We use these keywords and we do that every day, 24 hours. And so we are a little bit biased to these kind of scenarios. But when you go to more specific domains, people are really interested in these more complex relationships, how things are really related to each other. And then you need that kind of expressiveness at the user interface to really be able to address these kind of issues. From my point of view, that will pop up gradually, because people, they are well able to handle these short-tail queries and the scenarios, but now they see, well, there are other domains where we have additional needs, and they are currently not well covered by these keyword-based approaches. And therefore, I think not within 3 or 6 months, but in a midterm process, I see that that kind of issues will pop up, and then you need these kind of solutions in the end. Yes, please.
So it seems what you've described is a shallow domain-specific lexicon. Are there core semantic lexicons that, for example, know that a river has water and lake has water that you build this on top of? Do those exist, or is that just something else that is outside the domain itself?
You see, we have that separation between that domain-specific and a domain-independent one.
Yeah.
And clearly, one investment has to be put into first developing that domain-independent lexicon.
Right. For example,
and
what
clearly,
water sources are at a city? It would know a river's a water source, a lake is a river. Yeah.
And clearly, it depends on the application domain. So envision later on how much effort you put first place into that domain-independent lexicon, because that can be a huge effort, or you can limit that. Okay.
Yeah.
And therefore, you have to have some idea what would be, in the second step, the application domains you want to address in order to see how much effort is worthwhile to be put first place in the development of that domain-independent lexicon.
And this is part of your cycle where they can view queries and say, people are starting to ask about water. Maybe we'll just link water to the other entities or things like that.
You see, currently we have separated that process. So the domain-specific part is part of that iteration. Because we think that core part has to have some really good quality. So the question is whether you are really willing to let other people modify that, you know. So currently that is a rather controlled scenario where the experts are really looking into that kind of stuff. But clearly they can get feedback from these iterations. They may see that these kind of queries are not well handled, and they see that is not due to deficiencies in the domain-specific lexicon, but in the kernel, and then they have to address that.
Thank you.
Hi. I'm a little bit curious about, I mean, maybe I sort of missed something huge, but about of the relationship between the two portions of your talk, on the ontology construction, sort of with your Mediawiki stuff on the one hand and the natural language stuff on the other. Have you considered or tried out being able to generate some of the, underlying metadata or underlying semantic structures and so forth directly, like using machine learning or whatever, from the semantically enriched wiki and or Wikipedia, vanilla Wikipedia, or because it seems like there's a lot of manual effort, even facilitated, but that goes into the ontology construction, then a lot more manual effort that goes into the natural language construction. I was wondering if you can, leverage one for the other.
We see that high potential of having synergy between these two areas. Currently, what I have shown that Oracle system is not really integrated with our Semantic Mediawiki stuff. Why I put these two topics into one talk was that they both address the challenge how to come up with environments that are supporting a lot of people in providing the kind of semantics you need in the end to come up with the solutions. And that wiki environment would be one component in building up these background semantic information that you then might exploit, for example, in your natural language environments in the end. And what you have seen in that pattern-based approach for relation learning is one concrete solution we have currently available to plug in some learning mechanisms already into that wiki environment. But there is room for a lot of improvement. And there are a lot of techniques around in my group and all around the world with that learning stuff. And that is some incremental process of plugging in more of these learning stuff. But clearly, that is very promising. Okay.
Yeah, I mean, yeah, that's what I'm interested in. Right?
Just a quick technical question. Are you allowed to, in your relation form for annotating the wikis, you'd have belongs to Croatia, for instance. Can you insert an entire binary relation in there? Or does it always have to reference the page topic?
Well, you see, what we have currently focused on is that you start from your page, and then you define the link between the entity that is described on the page and the other things that are then related to that kind of stuff. But the mechanism in the end is not biased to have that directed notion, you see? Because in the end, you generate these facts in the background, and there you might link other things to each other, not only Prague to Croatia in the example. But currently, the kind of environment, because you are on that specific page, is somehow tailored to that situation. But the underlying techniques are rather generic.
Any more questions? So I'd like to thank Professor Rudy Studer once again. And if you guys want to meet him, maybe after lunch or so on, please let me know. I'll be happy to set it up. Thanks.
Okay, thank you.